topics I'm excited to get to today is degeneracy in the space of TLNs, bifurcation theory, and oriented matroids, and also kind of another aspect of bifurcation theory with oriented matroids, which we think about as a neuromodulation induced bifurcations. And I think I will just start by drawing maybe a little picture where we're really thinking today of the space of these networks, the space of TLNs. And if you will, particular CTLNs for particular graphs, say here's one graph, here's another graph, and so on. These are kind of points in the space and maybe partition the space in interesting ways. And now we want to think about kind of the relationship and the way that the dynamics of the network changes as we move through different points of the space. Okay, so I just want to kind of give this, it's not a beautiful drawing, but like a little bit of a big picture. We are now thinking of, you know, for lack of a better word, kind of the moduli space of TLNs or something like this. All right. Okay, so first let's review what TLNs and CTLNs are. And I believe most of you were probably here yesterday, but if not, I'll do a quick crash course. But the basic question motivating this work is the neuroscience question, which is how connectivity affects dynamics. How does connectivity shape dynamics? So we know that neural networks in the brain have very precise connectivity through, you know, that's been wired through a combination of evolution and development and learning, and this does something, right? This causes the networks to be able to support very interesting patterns of activity. So the model that has been very fruitful for us to study these questions, kind of a toy model, but it comes from the neuroscience literature, and it is threshold linear networks. And I just want to point out, so it's a very standard model in the sense that we have, oh, now the pointer's gotten weak. I'm going to go back to the stick. We have xi's, which are firing rates of individual neurons. This is the W and the B. W is a matrix, B is a vector of external inputs, or perhaps combined with thresholds. And then we have the threshold nonlinearity, which is also known as the ReLU in the machine learning world. So you pick a W, you pick a B, you have a threshold linear network, right? And the game is to understand the dynamics and in particular to understand how kind of the connectivity of the network shapes the dynamics. And these networks, we like them for a couple of reasons. Number one, they're very expressive. So they display the full repertoire of nonlinear dynamics despite being piecewise linear. So in my mind, it's kind of the simplest nonlinear model that has all of this rich dynamics with multistability, limit cycles, chaos, and even quasiperiodic attractors. You can see all of those for effectively inhibitory W, and that's, you know, that's a strength. They're very expressive as a family of networks. On the other hand, they're also mathematically tractable, right? And so we can prove theorems relating the structure of the W matrix, especially when it comes from a graph, to important features of the dynamical system. Okay, and I just want to quickly make sure we're all on the same page, right? So in a traditional Hopfield model, you have static attractors, which are stable fixed points. So the idea is, depending on initial conditions or some input to the network, the activity evolves to a stable fixed point, and that may represent some pattern, like a visual pattern or something that's been stored in the network that is then recovered. And so these networks do sort of memory recall with error correction and so on. But there are also dynamic attractors in threshold linear networks and in the brain, right? So we also see periodic patterns of activity that are quite meaningful and in fact essential to support functions such as locomotive gaits, breathing, and so on. Okay, so the subfamily that we have paid a lot of attention to in the past is combinatorial threshold linear networks, where you make your W matrix from a directed graph. according to a simple prescription. And these networks are effectively inhibitory. So there are two weights, weak inhibition and strong inhibition. These epsilon and delta are bigger than 0. We talked about this quite a bit in the lecture yesterday. So if you weren't there, I'm sorry, but I'm going to have to go faster through it today. But in particular, there are generalizations where the epsilon and delta can have a subscript j here and vary from neuron to neuron. And also, we have shown that these networks map onto EI networks, right? Where when you have edges, you actually have a positive value as a weight between neurons, and then there's a global inhibitory node. Okay, so there is a mapping between these networks and sort of honest to goodness kind of EI networks. And so let's keep that in mind. And so we really do want to think about the nodes in the graph as corresponding to excitatory neurons, right? And when there's an edge between them, there's an excitatory connection. And this weak inhibition is really the effect of excitation plus strong inhibition, right? And then the strong inhibition happens when there is no edge because that's just the background strong inhibition. Okay, so that's our setup. You can think of these as generalized winner-take-all networks. And the lovely thing about them is that for fixed parameters, when the activity changes, it's because the graph changed, right? The graph is really dictating the different patterns of activity. And so this is a way in a toy model to access connections between connectivity and dynamics in a very controlled way. Okay, and then these networks, again, have lots of fun behaviors, lots of fun attractors. So this is kind of a sampling. If you're curious or you want to play with these yourself, or you want to maybe have students play with them as part of a class or a reading course or something, Katie and I have packaged up code to make these pictures. The code is very simple because, basically you just have an ODE solver to solve the system of differential equations. And so most of the code is about taking the graph and applying this recipe to make your W matrices and also make the pretty plots. Okay, so just to make it extra easy, we've packaged that up. But a lot of people rewrite code for this. It's not hard. So the code part is not a significant issue. We think of these, so part of the reason these networks are so mathematically tractable is because we can really think of them as a patchwork of linear systems. And I want to encourage you to really pay attention to what's happening inside the nonlinearity. So you flip from the plus to the minus side, right? When the argument flips from plus to minus, that's happening along a hyperplane. So each one of those equations is the equation for a hyperplane where the W entries are kind of a row of the W matrix, and that's like the normal vector to the hyperplane. So these equations really look like n dot x plus b equals 0, if you want to set it to 0. So you get this nice hyperplane arrangement, and the game then is to, or sort of the first game, is to try to figure out what are the fixed points of this network, okay? To be a fixed point of this network, you have to be a fixed point of one of the linear systems that you get when you confine yourself to a chamber of the hyperplane arrangement, but also the fixed point has to live in the chamber where the linear system that defined it is controlling the dynamics. Yeah.
So on the fixed points,
yeah, so of course, if you consider the entire space of TLNs, you will have degenerate situations where the fixed point goes on the wall, goes on the wall between the chambers. So for our results, we tend to impose non-degeneracy conditions on the W matrix, which ensure that the fixed points are away from these hyperplanes, but they do tend to be on walls of the positive orthant, because the fixed points, what distinguishes them is their support. So if you have a fixed point with support, 3 of the 10 neurons, that's going to live on one of the boundary pieces of the positive orthant, right, where all the other neurons are 0 and only those 3 are non-zero. So they don't really live in the interior, right? But we do have them live away from the boundaries of these hyperplanes. Okay, so anyway, this is for a simple 3-cycle case. You have, with 3 nodes, you'll have 3 hyperplanes. With n nodes, you have n hyperplanes in Rn. and you get this nice arrangement, and that arrangement contains sort of all the information in some sense, or a lot of the information about the network dynamics. Okay, so we've had old results. I talked about these a little bit yesterday, so I'll kind of fly through them today, but just so you know, there are some technical results on these networks that have been sort of published before and reviewed in this review paper with Katie Morrison. It has a lot of the older results, so look at that if you're curious. In particular, we derived all these graph rules, which allow us to directly connect graph features to properties of fixed points, right? So these rules are saying things like, if your graph has, this property, or there's a node with this property, or a subgraph with some property, then there's going to be a fixed point in your network, or not, or it's going to be forbidden. Okay, so anyway, so lots of stuff, and I'm going to just keep this super short so I can get to the next part, which is to look at some phenomena that led us to degeneracy. So looking at the fixed points, so remember the stable fixed points, they're attractors in and of themselves, right? But the unstable fixed points, right, need not be important, right? You might say, why do you care about unstable fixed points? Your activity will never converge to an unstable fixed point, or like with, measure 0, it will converge to an unstable fixed point. And the reason is because they actually have a really strong influence in shaping the dynamic attractors. So this, in particular, the unstable fixed points that have kind of minimal support with sort of small subsets of neurons, they tend to correspond to dynamic attractors. And so just to give you a sense of what that means, so here's a very simple example that I also talked about yesterday, where you have a network with just 4 nodes. There are 3 fixed points, and these are the supports. 2 of them are minimal. They correspond to the 2 attractors that we see. And in general, right, there's kind of a rule of thumb. There's no proof here, but there seems to be a correspondence between these minimal unstable fixed points and the dynamic attractors. And it's very concrete in the sense that if you want to find the limit cycle corresponding to one of these unstable fixed points, all you need to do is initialize, pick initial conditions near the unstable fixed point, and then the activity kind of falls into the limit cycle. So it's a prescription for finding them as well, right? Which is, at least numerically, which is non-trivial in general, right? In general, you have a high dimensional space. You can't possibly sample all possible initial conditions, right? And so you can miss a lot of things. But this gives us a way of finding them. And then here was an example where you had a coexistence between stable fixed points, a limit cycle, and a chaotic attractor. And there was, this is just kind of an example of the correspondence where you had minimal fixed point supports, exactly 4 of them, and they do directly correspond to these 4 attractors that we see. Okay. Now, this led us to think about specific graphical motifs. Okay, now this is new stuff that I didn't talk about yesterday. Specific graphical motifs that support that have a full support fixed point associated to them. Okay, so the logic here is we have these competitive networks, right? The activity is kind of trapped inside a box. And if your system has a single fixed point and it involves all the neurons and it's unstable, if it's stable, you'll probably converge to it. But if it's unstable, right, then that sort of subnetwork needs to have a dynamic attractor, at least in isolation. Right? So for example, the 4 cycle here, as a subnetwork on its own, it has a single fixed point, it's unstable, and there's a corresponding attractor where the activity kind of loops around, so the neurons fire in sequence around, in the same order that they appear in the graph, okay? But also, for instance, this graph, which we call the 4-SIC-U, this will come up later as well. So this is a nice example where you have 4 nodes, 2 and 3 are bidirectionally connected. And this construction is actually what we call a cyclic union. So there's a particular building block way of thinking about this graph, which is not so important for today. But what you see here is that again, there's going to be a single fixed point of full support. All the neurons fire at that fixed point, but it's unstable. Okay, so again, this network in isolation, we expect a single dynamic attractor, right? In fact, we know there needs to be a single dynamic. We know there needs to be dynamic attractors, at least one, because there are no stable fixed points, and the network has to do something. And so by collecting these kind of minimal motifs that support dynamic attractors, then we can start to see them embedded in larger networks and decompose the larger network into sort of collections of these motifs. So, so this is kind of, these are all the ones on 4 nodes. And then also we do include the clicks, which are giving us stable fixed points. But these are all the sort of what we call core motifs on 4 nodes, right? So there are a lot more graphs on 4 nodes. So directed graphs on 4 nodes, there's like more than 220. I forgot the exact number. But only 5 of them, including the 4-click, have this property, right? That in the CTLN, there will be a single fixed point of full support. And only 4 of them have the property that that single fixed point is unstable. So we think of these core motifs as kind of like the atoms, right, of the network in terms of supporting attractors. Okay, so the question, so to go back to the main question of how does the structure of the, of the graph or of the network shape the dynamics, now we can ask a sort of a more detailed question. It's like, so by looking at the graph, we can try to, compute with graph rules, for example, what the fixed points are. We can look for the minimal fixed points, sort of, our heuristic is that there should be attractors associated to them. And then we can see how this process, how predictive this actually is of the attractors in kind of a larger graph. So we did, with Katie Morrison and some others, we did an exhaustive study many years ago where we looked at all directed graphs on 5 nodes, right, up to isomorphism. There are 9,608 of them. This number I'm sharper on than the number of 4. We did not go to n equals 6 because when you go to n equals 6, there are 1.5 million, right? So 5 was like a good number because 10,000 is kind of a manageable number of graphs that we can analyze and try to understand, but still rich enough, right, that it gave us a good sense of what's going on. So of those 9,600 graphs, about 1,000 of them had core motifs with a single full support unstable fixed point that survived to being a fixed point of the full network. Okay, so the survival rules are sort of settled. They're part of the graph rules. But in other words, just because your subnetwork supports a fixed point on its own doesn't mean that when you embed it in the larger network, that fixed point will still be there, right? So it could be that once you have the nodes firing at the rates that you need for that fixed point, it also turns something else on. And so on its own, it's not a fixed point actually. And so when the fixed point survives, that's when we expect the dynamic attractor to survive. Also, when the stable fixed point survives, we expect the stable fixed point to be there, but that's more straightforward. And so we use kind of our theory, this sort of idea, our heuristic idea of the correspondence between fixed points and attractors to predict what's going to happen in sort of all the n equal 5 graphs. So there were like 1,050 that were interesting, another 8,500 that were less interesting, where we only had core motifs corresponding to clicks, and we only expected stable fixed points in those cases. And then we went ahead and for different sets of parameters and sampling kind of as many initial conditions as we could think of, random ones, also perturbations around every fixed point, many perturbations around, we did like this battery of initial conditions to do kind of, as good of a sampling as we could come up with in order to find all the attractors. And what we found is that in all but 22 of the graphs, right, so 9,586 of the 9,608, we were able to accurately predict the attractors. And the mistakes were also kind of interesting, right? So sometimes what would happen is like the fixed point would survive, but the attractor wouldn't be there because its basin of attraction somehow shrunk to 0. And so there's some interesting stuff to be said also looking at the cases where our prediction went wrong. So that was, kind of a nice study. There's sort of pieces of it that have been published in papers, but there's also a package on GitHub that has this kind of the full classification that we came up with. Okay, so that was kind of interesting. So we could predict kind of these dynamic attractors. But then we discovered something unexpected. And this leads me to kind of the first meaty part of the talk, which is about degeneracy in the space of TLNs. So this was a surprise. When we did this analysis, we expected, okay, when there's a 3-cycle with a surviving fixed point, there should be like kind of a 3-cycle attractor, like a limit cycle, but it might be wonky because the embedding affects the shape, right? And so we expected like all of these attractors would actually kind of look different from each other, even if they came from the same core motif, because the embedding affects the dynamics. But in fact, we found large families of graphs where if I compared one graph to another, the dynamical system was different, right? So maybe one graph had 2 attractors or 3 attractors and the other one only had 1, but there were attractors in common that looked identical. Okay, so this is a little movie I'm going to play for you. These movies tend to be very boring, and that's kind of the point, like nothing changes, right? So on the left, you see a particular graph. So this is corresponding to a fusion 3 cycles. This is one of these attractors that we've seen before, where you have the neurons fire in the order of the 3-cycle, blue, green, gray. So you get this nice 3-cycle, but together with the gold, which is kind of firing almost like it's at a steady state, right? So we call this a fusion attractor because it's almost like you took a fixed point and a 3-cycle attractor and fused them together into like a bound state, which is like a new attractor in the, that's 4-dimensional, that has like all 4 neurons, okay? Okay, so that arises for this graph. This is a core motif. Okay, so the core motif on its own, then you have the 5th node is isolated here. This is a disjoint union of 2 connected components, but this is a graph where we see, and we expect to see, the fusion 3-cycle attractor, okay? But now when I play my movie, we're gonna go through a series of other graphs, and there are 49 in total, right? And other details of the dynamical system are different when I change the graph. But this particular attractor is there in all of them, okay? So you can see, let me see if I play. You can see the graph changing. Arrows in and out of that 5th node can change. You can see the transient dynamics change a little bit. This is the same projection everywhere. So the transient dynamics, but the attractor itself looks identical, meaning as a subset of R5, right, that limit cycle is exactly the same curve, okay? Even though I have really different graphs here. Christine.
Are you changing any of the edges that are in? So you had the base graph.
Yeah.
And then in the movie, it looks like you're just sort of layering on edges on top of the base graph.
I have the base graph, which is the core motif, which is common to all of them.
Okay.
But I'm changing edges kind of between that core and the 5th node.
Right.
In both directions.
Right. Yeah. And so the point is that, but you don't change any edges within the core.
No. The core motif is as an induced subgraph, it's identical.
Okay.
Right. So this is an example where the 5th node actually is silent in the attractor. So it's maybe not, but there are other examples where the extra nodes that are not part of the core do get engaged, and that pattern is also identical even as we change the edges in and out.
But so I'm understanding this as there are sort of variations on a theme in the graph. You have this theme, which is the core, which is the attractor, and it's realized by this sort of base motif in the graph. And then you're saying, here are all the ways that I could have additional edges which don't affect that core motif.
Which don't affect that core motif, right? But can affect other attractors.
Sure.
right? So some of the ones that we went through, I didn't sort of pause on a good one. Let's see. That's a good one. See that 2-click? There's another attractor. And for this system, it has this attractor, but it also has a stable fixed point supported on nodes 1 and 5 on the blue and the red, right? So we're changing the overall vector field, right? And because edges in and out of that 5th node can change, we're also tilting the hyperplanes, even the hyperplanes for those 4 nodes in the core, right? So we're changing a lot of things, but somehow this particular attractor, right? So as a loop, right? There's part of the vector field that doesn't change and other parts of the vector field that do change. And it's kind of interesting because it means that, first of all, you can alter basins of attraction without altering the attractor. That's not obvious because these are dynamic attractors, right? And so they have internal structure. And so you might think, oh, if I reshape the basins, I'm going to end up reshaping the attractor. But you can actually kind of separate that. And it kind of gives you a sense that, so I mean, okay, so maybe I'll use this picture. So suppose I have a network here where I have this, this particular attractor number 1, and there's a whole bunch of other networks that have the same attractor, okay? But these networks can also have other attractors. So this one might have attractor 1 and an attractor 2, and so on, okay? And so you're finding distinct points in the TLN space that have the same attractor, and it suggests that you might be able to sort of move in directions that preserve this attractor, but learn an additional one, right? So that's kind of like sort of a non-trivial observation, right? Because you might think once you have sort of a complicated, right, like this fusion 3 cycle, sort of a complicated pattern of activity, that if you add another thing on top of it, right, you learn a new pattern, you're going to screw this one up, right? And what this is showing is it seems like you can do that, right? But we don't understand super well how. Other questions?
Yes. So did you also see cases where the second attractor was kind of part of a different network, or is maybe 5 2 layers?
So there are plenty of networks that have that 4-5, that 1-5 fixed stable fixed point as an attractor as well.
Okay,
and so
that attractor is then also similar for.
Yeah. So if I say maybe all of these, I'm going to draw this kind of like a convex hole, and that's intentional, right? If I think all of these have attractor 1, this one has attractor 2, maybe this one also has attractor 2, right? And here there's a network that just has attractor 2, right? And so you have these different regions, and where they intersect, you have a network with multiple attractors. And so on. So it seems like the space has this very interesting structure, and there are directions you can move in, right, where you preserve one attractor, but maybe pick up or lose another one. And yeah, I mean, in light of like Catherine's talk yesterday about degeneracy, right, and symmetries, that she called it symmetries in the weights, right? To us, this is a very interesting case study where you can sort of try to study how changing the weights, which weights can you change, and which weights do you really need to freeze in order to keep the attractor the same. And it's not completely free. So it looks like I'm adding and subtracting. It looks from this one that all I have to do is keep the core graph the same, right? But in fact, that's not enough. So not every graph that has that embedded core graph preserves this attractor. So there are ways I can lose it. And so this is just now what I've shown you is kind of a computationally discovered family of graphs that do preserve this attractor. And we also, there's some hidden work in here to like align the graph. So we had to like find the right permutation of the nodes so that when the attractor is in there, right, that it shows up with the same colors and in the same order so that we can actually see that it's the same. So there's a lot of kind of hard work to get this, to get the movie to look this boring, basically. Okay. All right. So that's one example. And then here's another I'll just leave that example for now as the one I'll show you from the movie. But now let's go back to this 4-SIQ, right? So this is a graph where, you have this graph automorphism where there's a symmetry between 2 and 3. And in this case, the attractor reflects that symmetry because nodes 2 and 3 are synchronized. So you see the green and the gray are on top of each other in the limit cycle. Okay, so we, with my former student Juliana, we did something kind of interesting, which is to go ahead and take the trajectory generated by this graph, go ahead and take that limit cycle trajectory and fit a new TLN in the machine learning way, right? So backprop through time, right? So we take a trajectory and there are, backprop through time is a way where you can kind of, do a fitting of a network and to match a particular trajectory, okay? And so, she learned how to do this and came up with, and so what we wanted to check, first we wanted to use this as a sanity check on the learning of backprop through time, okay? So the initial idea is like, okay, well, if we started with an attractor that we knew came from one of our networks, right? And in this case, it's just I'm just looking at the isolated network, right? So I don't have the multiple graphs because that happened when I embedded it in a larger network, right? Here, I'm just looking at this isolated network, just 4 nodes. Now, if I take backprop through time and try to fit a new TLN also on 4 nodes, right? We were thinking we should recover the TLN we started with, right? Because we did not see degeneracy at this level. Like we only saw it in the embedded situation. And so she did that. And what she discovered was that she got a new TLN, okay? So here, this graph, right, is an induced subgraph of a larger graph. So it's sitting inside the larger graph in a particular way.
Okay.
So I'm not putting the nodes in some space. I'm just thinking of one graph sitting inside another.
I'll ask you more later.
Okay. Yeah. That's what I mean by the way the graph is embedded in the larger network. I just mean the way that the graph kind of is connected to the additional nodes in the network.
I was just wondering, like in these different examples where you see the same picture, are the nodes that are different? Did you notice anything about like the magnitudes of their firing rates? Like are they really tiny or something?
Yeah. So in this case, the 5th node, right, on this attractor, right, isn't firing at all, right? But sometimes, yeah. So usually the nodes that are outside the attractor are kind of have small rates, but depending on how, I'm not really playing this movie anymore, but so when I say depending on the embedding, so I would say all 49 of these are different embeddings of this fusion 3-cycle graph into the larger one, because they all connect to the 5th node in different ways, right? And non-isomorphically. Okay, that's what I mean. But there are ways that you could connect the 5th node that would distort the attractor or kill it altogether. Okay, and those are not part of these 49 graphs. I'm showing you the ones where it's the same. Okay. All right. So, all right. But anyway, so here we're not thinking of it inside a larger network. We're just taking a core motif, right? It has an attractor, and at this point, we don't know of any other TLN 4 nodes that has exactly the same attractor. Right, on 5 nodes, right, there could be families, but on 4 nodes, like this is sort of the only one we know. And so we thought that using, backprop through time, doing these automated machine learning things, that we might recover the same TLN, okay? And we do not. Caitlin. So we've done it in 2 ways. We've done it with all the parameters free, We've done it fixing the B's to B1 so that we're only altering the W's. And we've put in constraints. Sometimes we put in constraints to ensure the network is competitive, but sometimes we don't, and we get solutions with positive values that also produce the same attractor. Yeah, so we've done it in all kinds of ways. I say Juliana started this, and then Zilong, who's another student of mine, has continued, and there are a lot of kind of newer results and newer experiments for sure. So anyway, so the bottom line is she found a new solution, okay? And we're like, that's interesting. And it motivated this question of like, how is that new solution connected to the old one, okay? So the idea that we came up with was that maybe if you, so going back to kind of this picture, draw another one here, right? So you have, you know, W1, B1, that's our original CTLN that we had. And then W0, B0, this is the one obtained via machine learning. Okay, and the first idea was, well, maybe in the space of TLNs, we can see what happens as we connect from one network to the other. Okay, and we're connecting literally by taking convex combinations. Okay, so and you take the convex combinations just as you would with points in Rn, except now we have matrices and vectors. And so define Wt as 1 minus t times W0 plus t times W1. Okay, so it's the most naive, you know, thing that you could do is just like in the TLN space, connect your networks with a straight line. And then look at the networks in between. Okay.
So the T is not connected to the dynamics of the network, right? It's
sorry,
just a
yeah,
Just
we use T because, yeah, because it's unfortunate. I think in some write-up I have an S now, which is also unfortunate for other reasons. But yeah, that is not time. That is the parameter in the, you know, in the moduli space, right? That we're moving from one W to the next. Exactly. Okay, and at every point, every WT, right? So in between, we have these WT and BTs, and those are new TLNs that we haven't considered before. Okay, at every point, there's a new system. Okay, so what happened when we did that? So let me just show you an example. So here we're going between 0 and 1. The top is the ML fit with backprop through time. The bottom is the original CTLN matrix, right? And you can see it has just 2 values, 0 on the diagonal. It's like, it's a CTLN. And here's the B vector, which is constant for the CTLN, which was not constant for this fit. So in this case, we did allow both the B's and the W's to vary. And in between, this is a particular initialization. I think I'm starting this at t equals 0. So there's a little t equals 0 here. And so I start off by matching this to the ML1, right? And as I interpolate, I'm going to move towards the CTLN1. Okay, so what's going to happen? And there's the attractor. You see like small changes in the transient activity. But the attractor is there everywhere. You see the T is changing up there, 0.5, T is 1, and then it ends. Okay, so that attractor is preserved all along. All right, and this is why here I drew this as a convex hull, because in fact, like this process doesn't care where I got my initial solutions from, right? Whether it was ML or from my CTLN exhaustive search. We expect now, and I'll show you a sort of theoretical result in a second, that this phenomena will happen for any 2 points that have the same, any 2 points in the TLN space that have the same attractor. Caitlin.
Yeah, have you tried going outside the convex hull a little bit?
Yes.
So like letting T go below 0 or above 1? Like is
Yes.
it affine or convex?
Yes. That's this one. Next slide.
Okay, sorry.
T goes up to 6. No, absolutely. Thank you. Yes, that is a natural question. So it's like, there's no reason for us to believe, right, that it won't go beyond, right? We kind of found 2 networks that have the same attractor, and we don't know if we can stretch it. So here we've done, yeah, we've done everything. Zilong has done everything, I should say. This one I did, but I'll just show you what's happening here where T goes past 1. So same attractor, T is 0.9, 0.1. Now we've gone past 1. You see the transient dynamics are having some more changes. Now we're at 2. T equals 2.5, 2.7. Now we're at 3. It's still there, right? Still there. So we have a whole direction, a whole line, but soon we're going to lose it, I think. 4.8, 4.9. Ah, there. It's gone. It's gone. It's lost. Okay. To do these simulations, by the way, I'm always starting at the same initial condition, right? So that it'll like get into the same pattern and the pattern will align. Because obviously, like, if the, just because the attractor is the same doesn't mean my curves here on this page are actually not, going to align. I need to start at the same point to sort of get them to synchronize across different simulations for different networks. But yeah, so we don't, and we don't know what's happening for it to break down, but it definitely stretches beyond. Okay, so this kind of observation inspired, so obviously there must be like a mathematical reason for this. Okay, so once you've observed it, it turns out it's not that hard. This is very tiny. You're not going to be able to read the details, but I can, send them to you if you're curious. It turns out there's a little lemma that's not hard to prove, which says that if you have 2 TLNs, right, where at some point in the state space, they have exactly the same value for the vector, right? So each TLN defines a vector field. There's some point here and the analogous point here with the same x values where the vector is the same. Then it's going to be the same everywhere along the convex hull of those 2 networks. So for every WT in between or WTBT in between, that vector will be preserved, okay? It's a calculation. There's like a little trickiness, but not too bad. All fits on like 1 page. And that's enough to realize that like, okay, if I have a fixed point on 2 networks, that's a vector that's 0 in the vector field. At the same location in 2 networks, it's going to be preserved all the way along. But also, if you think about what a limit cycle is, right? It's like it's a parameterized family of vectors, right? At different points along your vector field. And so if all of those are the same, right? If you really do have the identical attractor on 2 ends, you're going to have the same attractor all the way through. So we should expect this, right? And it's one of the sort of nice things about TLNs. I actually had the thought at some point, well, maybe like in a deep network, you have a similar phenomenon, right? So maybe if you have 2 networks that generate the same function, the same input-output function, then you can take convex combinations, right? And every network in between will also generate the same function. That fails, right? So there's something about it's got to be recurrent like this. Once you have layering, this kind of breaks down. So it's not really expected. To my knowledge, like nobody has sort of seen this phenomenon before in kind of ReLU networks. But it's not hard to prove, and it's very cool. So what this means, so this is back to the 4SICU, the other attractor I really like. It means that we know in this family, right, where we found the 49 graphs that for the 4SICU, I'm not sure it was 49. For the Fusion 3 cycle, which is the first movie I showed you, it was 49 graphs. But anytime you find multiple graphs that have the same attractor, you expect every graph in the convex hull to have the same attractor, right? Because literally any two graphs you can connect, and it's an easy, generalization to see that everything in the convex hull is going to have the same attractor. So now you have these like, higher dimensional, not just 1-dimensional, but you have like these sheets in the parameter space where it's like I move in this direction and this attractor is preserved on the nose, right? Other stuff may be changing, but this particular attractor is preserved. And so in particular, if I want to learn something new and not screw up what I already encoded, right, I want to kind of move in those directions. But if I were doing, you know, machine learning gradient descent thing, and this was like one of the requirements, I probably wouldn't move in those directions because I don't change anything. Not for this attractor anyhow. Okay, so yeah, so I think this is maybe another movie. It's a quick one just to show it for another attractor. This is like, so like, it doesn't look like anything's happening, but you see the T changing. Yeah. I was so excited when I got this working and I showed my kids. I was like, look, they're like, Mom, nothing's happening in your movie. It's the most boring movie ever. I was like, that's the point. Nothing changes. Okay. Anyway, so we've done a lot of stuff like that. And there is a sort of upcoming paper with Zilang and Juliana. I think I lost his picture. Okay, I will show it to you at the end. But there's an upcoming paper where we classify kind of we try to find the full family of W matrices, right, for each of the attractors we see for the n equal 5 cases. And also prove it, you know, we sort of show these results, the theoretical results, and a few other little things. Okay, so now I want to get to my next story. Yeah, it took a long time. Everything takes longer than expected. Okay, which is the oriented matroids. Okay, so this really started. So, you know, we're still in this mindset of looking for what's happening in the space of TLNs. Okay, so we love the CTLNs because it allowed us to sample sort of really different points in the space dictated by these different graphs. But now we want to really fill it in, right? And fill out the story and understand the bifurcation theory in a little more detail. And for this, what we found is that oriented matroids are a very powerful tool. And this is work with Katie Morrison, who's been working with me for probably the longest on all this stuff, but also Chris Langdon was a postdoc we had years back. He's now, he's been in Tatiana Engel's lab now at Princeton for a bit. But when he was a postdoc with us, he pushed us to look at oriented matroids. I should say at the same time, I had a grad student, Caitlin, who's no longer a grad student, who's here, who is also sort of interested in oriented matroids for totally different reasons. And so I had, you know, there was this moment in my group, right, where I had a postdoc who was like, we really need to look at oriented matroids to study the TLN bifurcations. And then I had a grad student who's like, we really need to look at oriented matroids to study, you know, neural codes. And we're, you know, oriented matroids, they're everywhere. I was resistant for a while, and then I gave in, and then I decided I love them. So, but the game now is to think about, you know, really the full parameter space. And I love this like XKCD, right? Because when you change the parameters of your, you know, dynamical system, in this case tennis, right, you can have wildly different results. I think pickleball is not on here because that is outside the space of acceptable parameter changes. Okay, so what did we do? So we wanted to understand the following question, right? If you fix a graph, okay, and you allow your W matrix to change in a way compatible with that graph. So now my graph is going to sort of dictate which connections are the weak inhibition and which are the strong inhibition. But I'm not going to force this binary, I'm not going to force, you know, binary synapses and like only 2 values. I'm going to allow them to vary. And we wanted to know then what would happen to the dynamics, in particular, what would happen as you know, what would happen to the fixed points as you change parameters. So there's sort of 2, there's sort of a local and a global story, right? So locally, same architecture, that means we fix the graph G, and as we vary from one W to the next, in this case, we're keeping kind of B constant in the story, we can see bifurcations And those bifurcations are like the simplest ones to track are the ones at the level of the fixed points. So it literally can be you have a fixed point and it splits into two, or you have two fixed points and they join into one, right? You have like creation and annihilation kind of stuff, or you can have two fixed points come out of nowhere, right? And so all these different things are happening and we wanted to understand them. And this was kind of the project that Chris had. And we told him just focus on n equal 3 for starters, right? That should be simple. And then we'll move up to 4 and 5. 3 was actually hard enough, but this was, this is a very ambitious project to actually try to understand the full bifurcation theory for n equal 3. So, so Chris, thought about this for a while and decided, what, we really could make use of oriented matroids. So oriented matroids is an area of combinatorics. It's fairly old by now. It is still, I think, fairly niche. So most people, including most mathematicians, wouldn't necessarily be able to define an oriented matroid for you on the spot, or maybe haven't really heard of them. And but it's a combinatorial object that grew out of a desire to understand the combinatorial structure. Combinatorial structures arising from several natural settings, one of them being hyperplane arrangements, okay? So in other words, when you have a hyperplane arrangement, let me just draw very quickly this picture. So just a set of hyperplanes in space. So in this case, I don't know, something like this, okay? Each hyperplane, so call this H1, H2, H3, H4, say. Each one you can orient. So you put a plus side and a minus side. Okay, and then the chambers of the arrangement, right, can be labeled with these sign vectors. So for instance, this chamber is on the plus side of hyperplane 1, the plus side of hyperplane 2, the plus side of hyperplane 3, and the minus side of hyperplane 4. Okay, so you can label all the chambers this way, and then you get kind of a, I would say, bag of sign vectors. Okay, and that collection of sign vectors, if it comes from a legitimate hyperplane arrangement, it has structure. Okay, it can't be any collection, right? So if I have, and so there are rules, like if I have plus, 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 minus, and plus, plus, minus, plus, like, I'm going to get these wrong if I'm making them up on the spot, but then there's like another vector that you have to have in between. There are all kinds of rules that this collection of sign vectors has to satisfy, okay? And these rules are inspire the axioms for oriented matroids, okay? There are also rules that independent sets of vectors have to satisfy. I mean, there's many, many other settings, I should say, and they're all equivalent, and it's kind of a mess, so it's like, oh, you can define oriented matrix this way or this way. There's like 5 different ways, and then there are theorems showing they're equivalent and so on. But I think the easiest way to get a sense of it is this kind of covector picture where you have these collections of covectors and you see that they have to satisfy rules. So equivalently, right, when you have a hyperplane arrangement, you can also look at a different presentation of the oriented matroid via what's called the chirotope. Okay, so geometrically, I think the easiest thing to think about is these sign vectors and the rules that they satisfy. But practically speaking, for us, what was easiest was to think about the chirotope presentation because that has all to do with determinants. Okay, and it's just like much easier to sort of automate the machinery. So we have threshold linear networks. I made this big deal at the beginning that the threshold linear networks have these hyperplane arrangements. These hyperplane arrangements can be characterized by collections of normal vectors like this. So these are the rows. This is like the ith row of the W matrix. Each one of those rows we can call, we can codify as one of our vectors. And then we can throw in the standard basis vectors. We've lifted everything up and we've homogenized. So there's some extra dimensions. There's an n+1. And we get a system of vectors that is defining our hyperplane arrangement. Okay, this lifting up is because our arrangement is not central, and then we can make it central one dimension up. So once when you have a collection of vectors in some Euclidean space, you can define the chirotope as a map between sort of n tuples, or in this case, m plus 1 tuples of those vectors, and 2, 0, and plus or minus 1. Okay, and what you're doing in the map is you're really stacking the vectors next to each other in a matrix, taking the determinant, taking the sign. Okay, so I have, some, larger number of vectors. I take subsets of n plus 1 of them in this case, because I have this homogenized setting. So n plus 1 is the dimension of my ambient space. And for every subset of n plus 1 vectors, I have a determinant and I have a sign. Of course, they're ordered, right? So if you switch their order, you're going to flip the sign and so on. And so a lot of these, this map has to satisfy a lot of properties, right, that the determinant has. So, to make a long story short, we're able to take the vectors defining the hyperplane arrangement, turn it into a chirotope, okay, and immediately start getting mileage in terms of the dynamics of the network, right? So observation number 1, this is proposition, is that the chirotope completely encodes the collection of fixed points. So if a subset of nodes co-fires at a fixed point, so sigma and fp of omega b of wb, and sigma is the collection of nodes, so some subset of the neurons, then that is going to be true if and only if certain chirotope elements satisfy certain relations with each other. Okay, so in other words, you take your hyperplane arrangement, pull out these vectors, form the chirotope, compute all those determinant signs, right? You can then read off, right? And you will, do this on an automated way on a computer or something, but then you can read off who your fixed points are. Okay, so that's lovely thing number 1. And this also, but there are more chirotope elements than what define the fixed points. And so there are some special ones that define the fixed points for us, and we call these the special determinants, and they have this form. I really don't have time to get into details because it's already 5 o'clock, I think. But let me just skip to kind of something really lovely. So not only do the signs of the determinants that make up the chirotope characterize which subsets support fixed points, but also the actual values of the determinants give you the values of the firing rates of the fixed points. Okay, so it's worth looking at the determinants beyond just their sign and actually tracking the real values of them, because that will give you the firing rate vectors. Okay, so there are simpler ways to figure out the firing rate vectors. Why would you do it this way? Because somehow now the chirotope, right, is encoding the combinatorial geometry of the hyperplane arrangement. And as we vary parameters in our W matrix, we can see where the oriented matroid changes. And that's going to lead to changes in, potentially, right, changes in the fixed point structure. If the oriented matroid does not change, we know the fixed points stay the same. So already we've learned something about the bifurcation theory. And then sort of maybe the last comment I want to make is there are, the oriented matroid axioms in this setting translate to relations between the signs of these determinants that can be read off from the so-called Grassmann-Plucker relations. Okay, so this, by the way, is just a formula that's true of any determinant. Okay, so everybody has computed determinants in the past. You put in, d vectors, say, that are d-dimensional, and you get a determinant. You stack the vectors into a matrix. If I take a product of 2 determinants, it's going to be the same as the sum of the products of these pairings where I do these swaps and swap a vector from one into the other. These are the so-called Grassmann-Plucker relations, which next time I teach linear algebra, I will make a point to include. And so it's this lovely relation, which actually is the kind of linear algebra manifestation of the oriented matroid exchange axiom that you see in the context of chirotopes. And what this means is that you have entanglement relations between these signs, which translates to entanglement between the fixed points. Right, so I like to think of the fixed points kind of like particles of my system, right? And they're entangled. Like if this fixed point disappears, like another one has to disappear or appear, right? And so there's these relationships, and the Grassmann-Plucker relations give you relations between the chirotope elements. And putting all of that machinery together, with Chris, we were able to come up with a complete classification of the bifurcations that can happen at the level of fixed points for all the n=3 graphs. So this is, by the way, you imagine you have your three-dimensional TLN space. Every W matrix has a corresponding graph. So this is a partition into 16 pieces of your space. And depending on what the graph is, we now can tell you, as you vary your W matrix, these are all the sort of fixed point configurations you can have. So you can test this, right? It's like make a matrix in MATLAB or something, or Python, a 3x3 matrix, figure out what the graph is, and then you can look at this table and you can say, oh, I'm either going to have a single fixed point supported on nodes 2 and 3, or a single fixed point supported on nodes 1, 2, and 3, right? And it also tells you which parameter to vary to go between them. Okay, so it's, it's a lot of detail, which we can get in n=3, but in other, higher order, we're still kind of working on what are the best ways to generalize this. Okay, so I'm gonna wrap things up here, and I just wanna, unfortunately, I can't get to the last story, but there's an oriented matroids part 2 that I'll just say like 10 seconds about. This is joint work with Nikki Sanderson, who's here, and Anna Digitatsu, and we then started studying what happens if you fix your matrix W, but vary the B vector. So this is a neuromodulation story, because now we're thinking about the network is in some sense fixed, but the inputs, right, and the modulating inputs, the Bs, are changing. And in this case, right, you can also wonder what's the bifurcation theory as a function of those changing Bs. And it turns out that you can also, first of all, you can get really cool looking attractors by doing that. You can see that the same network, same W matrix, as you vary the B, can have different dynamic regimes where you might have a single stable fixed point, and for one value of B, this beautiful dynamic attractor for another value of B, and different kinds of things going on. And it turns out that answering these questions about which networks have dynamic attractors as you vary B, and how does the space break up, and so on, also benefits from an oriented matroid, a different one than the one we had in the previous project. Okay, and using oriented matroid machinery here also allowed us to kind of understand the n=3 case with a lot of detail. Yeah, we have all this work that I'm not going to get to talk about, but I'm just kind of advert. This exists, and it's also very cool. As maybe a second story to convince you that oriented matroids are really powerful. So I'm going to just wrap it up now, saying thank you. These are so I have more collaborators and more former students than this, but these are the ones who all worked on in some way, shape, or form on TLNs. The first story about the attractor moduli spaces was with Juliana and Zilong. So Zilong is still a grad student of mine, and who's been working on mapping out which families of W matrices have which attractors. Katie and Chris were the ones involved in the first oriented matroid bifurcation theory work, and then the work I didn't get to talk about with Nicole and Anda, and I think that's it. Thank you so much.